Alright, we're going to look at the final stage of cellular respiration. Okay, I'm going to abbreviate it ETC, but it's the electron transport chain. Okay, this happens in the inner mitochondrial membrane. Okay, so inner membrane of the mitochondria. So inside the mitochondria, you have all this membrane folded up in there. Right? Did you guys remember looking at that? Okay. Yep, just like our intestines. And the reason for that is because our electron transport chains are all throughout that membrane. So the more you can stack in there, the more chains you have. That means the more energy you can make. Okay? So that's why the mitochondria are like that. It's like trying to put as much as you can in a box to go somewhere. Okay? It's trying to put as much electron transport chains in there as possible to create as much energy as possible. All right? And depending on where you're at in the body, you're going to have more mitochondria than others too. So some cells can have 50, over 1,000 mitochondria, and some cells can have 50 mitochondria.
Is the citric acid?
It's in the matrix of the mitochondria. Mitochondria matrix, same as the intermediate. Okay, so it's in the inner membrane here. This is where all your NADH and FADH2s are coming. Okay, so think back to how many NADH we had. Can anybody remember how many total NADH we had?
4. 2 happened in glycolysis, and then we had 3 in the and 6. 2 happened in the intermediates. 3 and 3, so 2. Okay, 5 each.
So it'll be 10.
How about 10? So we had 2 in glycolysis, right? Correct?
Yep.
1 per pyruvate in the intermediate step. But how many pyruvates do we have? 2. So that's 2 total. And then 3 per acetic acid in the citric acid cycle. And how many of those do we have?
6.
2. So 2 times 3 is 6. Okay. So per 1 glucose, you're going to get 10 total NADH. So for 1 glucose, 2 in glycolysis, 2 in the intermediate, and 6 in citric acid. Okay, that's 10 total. All right. Now we're also going to get 2 FADH2s. Okay. All right. Those are all going to bring the electrons and hydrogens to the electron transport chain. Okay. That was their purpose, to rip the electron and hydrogens off the molecule and take them to the electron transport chain. Okay. Here's our beautiful electron transport chain. Okay. I had the best artist in the LCC art class draw this for me. Just kidding. These are my beautiful drawings here. So the electron transport chain is actually just a bunch of proteins in the membrane. Okay, just a bunch of proteins in the membrane. And your book has a pretty good drawing of them. Okay, pretty good figure of them. What's going to happen is you're going to have NADH come in here. And it's going to send its electrons through the membrane here. So it's going to shoot its electrons off through the membrane. Okay, the electrons are going to go through this membrane and then out right here. Okay, they don't make it all the way to the final one there. Okay, so the electrons flow through the membrane. It's what they call the fall of the electrons. We're not going to go into that, but you may, if you ever read any other sources, they may call it electron fall. Okay, we're controlling the flow of electrons because electrons are very energetic, right? Okay, they're all over the place. Okay, like a little 2-year-old boy, they're all over into everything. We have to control that movement down the membrane. I saw a lot of nods when I said 2-year-old boy. Okay, as the electrons go through that, it also, because it's really energetic, releases energy. As electrons move, it releases energy. And when it does that, all the hydrogens that were on NADH get pumped across. So we actually end up pumping all these hydrogens across. All right? So we brought the electrons in, they go through the membrane, all the hydrogens we brought in get pumped across. Now, FADH2 does the same thing. It just starts a little later in the process. FADH2 kind of starts right here, just a little later in the process, but it does the same thing. Okay? And it also pumps all its hydrogens across. The energy from the electrons do. We just keep pumping them across. So now all of a sudden we're going to have tons of hydrogens over here, correct? And not very many on the other side, right? So what does nature tell you about that? If you have a ton of something on one side and not very many on the other side, what's going to happen? They're going to want to come back down the concentration gradient. Now, unless we open a channel, they can't. So what happens is we get to this very last protein, and it's a channel form. And it's open. And these hydrogens actually, they just imagine a bunch of cars flying through a tunnel, okay? They just take off and zoom through. Okay? They take off and zoom through. Now, as they zoom through, they give off energy, okay? As they zoom through, they give off energy, and I'm going to use the next page just to write this out. They give off energy, and that energy is used by the enzyme we call ATPase, which is just shorthand for ATP synthase, okay, which is just an enzyme that makes ATP. ATPase uses that energy from the hydrogen zooming back through, right? If you stand next to a car that's going 70 miles an hour, you feel the energy coming off, right? So think of it like that. All these hydrogens flying back down their concentration gradient, excited to even it out. Enzyme gets that energy and uses it to make ATP. And what happens is you have an ADP sitting there and you have a phosphate sitting there, and this enzyme comes in and makes ATP. It reattaches the phosphate back to ADP and makes ATP. Okay? So it reattaches the phosphate back and makes ATP. And this is going to happen 32 times in the electron transport chain for one glucose molecule. Okay? So adenosine diphosphate, di meaning 2, gets reattached to the third phosphate using that enzyme. Because phosphates are really negative, right? Phosphates are really negative. So imagine like when you try to push two magnets together, right? You take the negative and positive sides and put them negative, negative, positive, positive. What happens? Right? They repel each other. So that's what this enzyme has to do, is it has to force this phosphate back on. So that's why we need energy and an enzyme, because it's really hard to do. So, and that's why it's full of energy though, because it's ready to spring out.
So the enzyme's there, but that enzyme is using that energy to connect that.
Mm-hmm.
Okay.
Yep. And so it does that to create all that ATP. Okay. And we needed those electrons and hydrogens. So glycolysis, intermediate Krebs, it's all just preparation for the electron transport chain. Okay? I know we make a little bit of ATP, but we don't make much. All right? Until we get to the electron transport chain. Now you're asking where the... Nope, this is all just... Yep, this is the culminating event. We did times 2 on... we showed the times 2 when we did that. Okay? So now you're asking me, where does oxygen come into play? Right? Who's thinking that? Who's thinking, why the heck do we need oxygen? Oxygen is actually what pulls those electrons down the membrane. Okay? Oxygen is what we call the final electron acceptor. Write that down. Oxygen is the final electron acceptor. Okay? It's your final electron acceptor. So at the end here you have oxygen sitting here. And it's going to accept the electrons coming down right here. Right? Electrons came down. It's going to accept the electrons. It's also going to accept these hydrogens that are coming through. So if it accepts the electrons and the hydrogen, what does it make, you think?
Water.
Yeah, it's going to end up making water. And that's why we get water at the end of cellular respiration. At the beginning, remember I drew that up like an hour ago? ATP and water. This is where we get it. Oxygen collects all those electrons, collects the hydrogens, and we get water. Okay, without oxygen, we have nowhere for the hydrogens and nowhere for the electrons to go.
So
So we wouldn't have ever even got to this point, and I'll show you what happens in a minute. Okay? So that's the electron transport chain. Now let's look real quick at total tallies, kind of what we're looking at ATP-wise, all right? So in glycolysis, how many net ATP did we make? So in glycolysis, we made 2 ATP. How many NADHs did we make in glycolysis?
10.
In glycolysis?
Sorry.
2. 2 NADH in glycolysis. Now, what they figured out over averages and just years of research is they figured out that an NADH from glycolysis, okay, is worth 2 ATP. Okay, an NADH from glycolysis is worth 2 ATP. So we'd go 2 times 2 here equals how much? 4 ATP. Okay? And there's more reasons of why it is that way, but we're not going to get into it. Okay? It has to do with how that NADH actually gets into the mitochondria. All right? Now let's look at the intermediate step. In the intermediate step, do we make any ATP? No. But what do we make? We make 2 NADH. Now, the intermediate step occurs in the mitochondria, right? So it's actually worth, for each NADH, you make 3 ATP. So how many ATP is that? 6. Okay. Now, citric acid cycle, how many NADH do we make?
6.
Yep, 6 NADH. 6 times 3 is what? 18 ATP. We also get 2 ATP in the citric acid cycle. I'll put that there. Okay. Just out of the process, we get 2 ATP. And then we also create 2 FADH2s, right? And those are worth 2 ATP as well, so we get 4 there. Okay? Oops. If you add all that up, what do you get?
32.
36. 36. 18 plus 2 is 20, plus 6 and 4 is 30, plus 4 and 2 is 36. So that's your total ATP count and where it comes from. Okay? So that would be good to memorize, to know. Okay?
Even the last name of the 6 and then the 2.
So 6 comes from intermediate step. 2 times 3 is 6.
Okay.
And then the 2 below, it's just the 2 ATP we get directly from citric acid cycle. Yep, so at the intermediate we get 2 NADH. And then you times that by 3, you get 6. And then at the citric acid cycle, you get 2 ATP directly. Yeah, just through the process, you can make 2 ATP. And then you get 6 NADH times 3 is 18. And then 2 FADH2 times 2 is 4.
Do we
Okay.
have to know why multiplied by 2 or by 3?
Yes, know the difference there. And the difference is just that glycolysis occurs outside of the mitochondria, and so it actually has to expend some energy to get it into the mitochondria, and so that's why it's worth a little less. Okay, so that's why you just need to know that one's worth 2 and one's worth 3. Okay,
Why are multiply it by 3?
that's how many ATP each one's worth.
So it yields 3.
Yep, 1 NADH will yield 3 ATP. Yep. So that just multiplied by 3. Yep, but that's a good chart to remember there. Also, you should know that, let's say if I give you, and this was on the quiz, okay, if you took it early, you may have struggled with this part of it. If I said, hey, I'm going to give you 2 pyruvic acid, tell me how many ATP you would get if you just threw that into where pyruvic acid would go in. Okay, you would have to calculate, figure out where pyruvic acid come about, right? So start from there and go, okay, because it's not that that's ever going to be the case, but it makes you have to understand the process rather than just memorize it, okay? So if I said, hey, you get how many ATP would we get from 1 acetic acid? Well, where does acetic acid come into play? And then go from there and figure out how many ATP would come about, okay?
So basically, you just nothing before it.
Exactly.
At that point, okay.
So I may give you a problem, hint, hint. You may get a problem on the exam, hint, hint, where I may say, you have 1 glucose, 3 pyruvic acid, 2 acetyl-CoA, blah, 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 3 NADH, 6 NADH, whatever. Tell me how many total ATP you would get from all of this. And you would have to know where each one begins and how many total ATP you'd get from that. Okay? So make sure you understand that. And there's on the study guide I'll put online, there's actually a sample problem.
Like
Okay?
starting from there and then going
Yep.
from each one?
Yep.
Even if they start at different levels and then adding all those up?
Yep, exactly. Yep. If I give you a glucose, that's easy. You can just remember how many total.
So why does it multiply in glycolysis only by 2, but then in the other 2 we multiplied it by 3?
And that's the end of cellular respiration.